Hello, my name is Christine Cho, and today I'm here to talk about how we used a tool from topological data analysis called persistent entropy to analyze Conway's game of life. Conway's game of life is played upon a two-dimensional grid, and once you pick an initial pattern, the pattern progresses by following two simple rules. But you can see here that from these two simple rules, a lot of complexity and chaos can emerge. Here's a simple example of a game of life being played, and you can see that the very first pattern and the very last pattern are identical. This is what we call an oscillator, and to be specific, this is a period 3 oscillator. Now, it's really easy for us to take a look and say that visually the first pattern and the last pattern are identical, but what if we had really complex patterns or patterns with really long periods, or what if we wanted to analyze hundreds of patterns at once? In that case, it would be really nice if we could turn these patterns into numbers. What we did was we took the input of an image of the pattern and we did some filtration and found the persistence barcode from that filtration. And once we had the persistence barcode, we could calculate the persistence entropy. And that is how we went from getting an input of an image to an output of a single number that summarizes the topological features of the input image. Now, what can we do with persistent entropy? Well, let's go back to the initial example of the period 3 oscillator. And here you can see that I can calculate the persistent entropy for every single pattern in that sequence. And just like how the first and the last pattern are identical in shape, the first and the last value of the persistent entropy are identical. And if we plot that out, we can see that we have a periodic graph. So what we did was calculate that persistent entropy graph for every single pattern of a given period. So let's say we had 200 patterns that were period 2. We calculated the persistence entropy graphs and found the range by subtracting the minimum from the maximum value. And once we had the range of every single pattern in a period, we could construct a box plot. So over here, these are the box plots of all of the periods that we had in our repository. And you can see that the median value increases in the beginning and sort of levels off. So that's kind of something that we expected to see, because initially, when the periods are very short, there aren't a lot of iterations for the pattern to evolve and change from that initial pattern. And so we can expect to see that the range of the persistence entropy will be sort of small in the beginning, and then it got larger as the periods got larger. Something else that we could do with having the persistence entropy values was we could decompose the persistence entropy values to find the subperiods. So as an example, we created a combination pattern of a period 2 pattern with a period 3 pattern, and that created a combination period 6 pattern, which is in black on the top. So you can see that when we took that combination period 3 persistent entropy graph and we did the fast Fourier transform on it, we were able to recover in the frequency domain the period 2 and the period 3 subperiods that composed the combination period 6 pattern. So that was a really cool finding. In conclusion, we were able to take the and transform from the shape space into the number space by using persistent entropy. And the value of that was that now that we had these numeric values, we were able to do data reduction and condense hundreds of patterns, thousands of iterations into a single graph to observe trends. And in addition, we were also able to apply existing analyses like the Fourier transform and find subperiods. And overall, we've demonstrated the potential of persistent entropy as an effective tool for analyzing Conway's game of life. Thank you, and I hope to see you at my poster.